Hi, it's Dave. Welcome. Today I'm joined by James Douma, an AI expert, a frequent guest on my channel. And today we're going to be diving into Tesla's supercomputer that they're using to train their neural nets. It's called Dojo. And we're going to do a deep dive into this, really kind of examine what it is, what kind of benefits it presents Tesla, what type of performance benefits, and what's the long-term impact on Tesla's kind of autonomous driving and humanoid ambitions. So welcome back on the show. James, how are you doing?
Great to see you again.
Awesome. So James, I'm curious, like, why did you choose kind of Dojo as kind of the first topic to kind of dive deep into, for an interview with me? And kind of in the bigger picture, like, yeah, I mean, why did you choose Dojo over, let's say, the neural nets or the architecture or other parts of AI day that they presented?
That's a place to start. Well, I hope that we eventually get around to talking about the other stuff. Dojo is interesting. I think it's going to be a really significant component of what Tesla does if things work out the way Tesla hopes they do and the way that I hope they do. I'm really interested in the stuff that Andre presented, the architectural stuff. A lot of the simulation stuff is really interesting. And of course, the Tesla bot potential is all really interesting also. But the Tesla bot is kind of vague. We already talked about it a little bit. So it's a little bit harder to sort of talk about in concrete terms. The architectural stuff I'm super interested in, but it's going to take more background research to be able to do a good talk about that. It's kind of time consuming to do all the background because there's a lot of papers I wanted to read and understand. And Dojo seems to get a lot of interest from people at least in my social media feeds. They seem to be talking more about Dojo than they were talking about anything except the Tesla bot. So the Dojo, I kind of felt like I could get the background work on that done pretty quickly. So I thought it would be a good place to start. And people are interested, and I could get it done pretty quickly.
Awesome. So let's do kind of a spoiler kind of alert, or just kind of let's share the bigger picture conclusion first, so that people kind of get
Okay.
a better idea. Some people might claim, hey, Dojo is not that important, or it's not that differentiated, or some people might say, Tesla is way out of their league. They're going into this hardware chip just think supercomputers that they don't need to or they should. It's a distraction. But as you dive into like, what is your main takeaway from Dojo? Like, is it legit? Is this going to actually work? Is Tesla just going to have so many problems and headaches, trying to make this work that it might not be worth it? What's your kind of take?
Well, it's legit. It's Dojo is a very meaningfully different way of approaching the problem of training neural networks. So if what Tesla was trying to do is just basically out NVIDIA, or essentially doing exactly what somebody else was doing, then yeah, it's a long road to hoe. The people who have been working in this space, who have their particular architectural niches staked out and they're working on them, like, none of these people are stupid. It's hard to like do better than they are at the things that they're doing. But neural networking is actually a really young discipline, and there are very few, and I think it's probably accurate to say none, that there are no architectures for large computers or die out there that are commercially available that are pure neural networking things. Like all of the architectures that you could get, that you could build a big computer around, they're architectures that were originally developed for some other purpose, which have been adapted to doing neural networks. The thing about neural networks is they are unusually homogeneous in the type of computation that they do. And because you can build a computer to take advantage of this homogeneity, and you can get big advantages. Like there's a lot of low-hanging fruit if you're willing to completely start over. And so Google has the TPU that they've developed, and that was definitely an architecture that was developed after neural networks came out. It's only designed to do neural networks, and it's a great architecture for doing neural networks. But of course, the only way you get to use that is if you go to, you have to rent it from Google. They don't sell those chips, and you can't build a system around that stuff. Also, Google needs to train neural networks, but much more than they need to train neural networks. They need to run neural networks like in a data center. So a lot of their architectural choices are things that aren't necessarily the right thing for a company like Tesla, which basically wants to do a lot of training, but they're not going to be running huge neural networks primarily, in the data center that they have. Their neural networks go into an embedded system out in the car somewhere in the world. And so the application space is a little bit different. It's also true that it's been a few years. So Google started on the TPU pretty much right after. I mean, Google's first TPU came out in 2017. As far as we know, the architecture hasn't changed. It's a stochastic multiplier, basically. It's a gigantic stochastic, systolic multiplier, and which I won't get into the details of what that is, but it's really good at a certain type of computation, assuming a certain space of constraints, which is a really good fit for Google, and it's not quite as good a fit for Tesla. The subsequent generations have tended to follow on that architecture. It's really good at what it does. They started really early working on that architecture after ImageNet, the big moment back in late 2012 when neural networks really broke out. But there have been advances since then, and Google's now they've got their architecture. They're not stuck with it, but they haven't really evolved it much. And so this is also an opportunity for Tesla to basically look at what's happened in the last 5 years and pick an architecture that is maybe better for that than the systolic multiplier, which is the core of what the TPU does. So I don't know. Anyway, you're going to have to tell me if I get too into the weeds.
Yeah, no, this is good stuff. So
okay.
What I'm getting so far is kind of like Tesla is looking for something more specifically suited for their neural net training needs. Google's TPU cluster there is not first adequately, let's say, customized and suited for their needs, but also it's a walled garden. Like Google's gonna do their own stuff. They have their own autonomous driving ambitions as well. So Tesla's options, would you say they were limited to kind of using kind of NVIDIA's GPU chips into a supercomputer cluster, or they would have to develop something themselves custom wise? With
the realistic options right now that Tesla has probably are to do an HPC with NVIDIA stuff, which is, we know that they're doing it. They revealed numbers on 3 clusters, and recently they talked about their 5760 node HPC or 5760 GPU HPC that they're building based on the latest and greatest NVIDIA stuff.
HPC meaning high performance cluster.
High performance computer.
Okay, computer.
So basically a really big computer. I mean, today HPCs are basically you take a bunch of computers and you connect them together with a network fabric, and then you run all the computers together to do a single calculation. I mean, that's what HPC is today. There was a time in the past when people built like single really fast processors, like the early Crays were built that way. But nowadays, the only way you get really fast is if you go really parallel. And when you parallel means you have lots of units that are identical and they all work together on a problem. And so HPC computers are basically computers that have lots and lots and lots of nodes, which might be CPUs, it might be GPUs, it might be other kinds of specialized things. And they're all connected together with a high-speed fabric, and they run software that treats them all as a single machine. So you have one problem, it breaks it up into pieces, it distributes it to all of these machines, and they collectively work to solve a problem. The reason you want an HPC is because you want an answer to a big calculation and you want it fast. Because obviously, if you're willing to wait 10 years, a desktop PC will eventually get there, right? And if it's not a big calculation, you don't need a big computer. So HPCs are to run big calculations and to get an answer soon, where that soon is not a month. There are calculations that people use, like there are nuclear simulations and weather simulations and climate simulations where people will use an HPC and they'll run a single calculation for a solid month on it. But in commercial applications, typically you want your answer in like 2 weeks or something like that, unless it's something like drug development where you can wait a couple of months and it's still relevant.
So with Tesla, they've been using, it appears, like NVIDIA chips into their own clusters. What kind of problems do you think that they've encountered that's kind of motivated them to develop their own kind of architecture for a supercomputer? So
neural networks are an interesting phenomenon in that they are, you can pour infinite computation. Like the more compute that you give a neural network development process, the better neural network you can make. So so one way to get a really good product or to get a really good neural network is to basically use a lot of resources on it. So you can make a big neural network and you can train it on a ton of data. Now, most things in the computer world, they get into diminishing returns at some point. Like there's only so big a computer, only so big a calculation that's useful because there are boundaries on various aspects of the problem. And neural networks are kind of unusual in that the sky is the limit. If we had 1,000 times as much compute or 1,000,000 times as much compute, we could actually use it. I mean, we could use it with it would take a little while to develop the software and whatnot, because the software that we use on HPCs today, it's designed for the size of the machines that we have. So you wouldn't be able to use it tomorrow. But the thing is, the techniques we have right now could use that stuff. So people who are developing really cutting edge, really big neural networks, they're totally compute limited. So a company like Tesla developing a product like FSD, they want as much compute as they can get. And you end up being cost constrained because you can spend billions and billions of dollars doing these computations as part of what you're doing. So you want a big computer so that you can get your answers fast, and you want it to be economical, right? So basically, if you feel like you might want to do 100 times or 1,000 times more compute than you're doing, and you're already spending hundreds of millions of dollars, well, obviously, you're not going to spend hundreds of billions of dollars. You're going to look for the thing that gets you the most compute for the dollar. So Tesla's going to be interested in a machine that can get them answers to sizable network training things relatively quickly. Like, it's not the case that they care so much about economics that they don't care how long the answer comes. Like, they're constrained. They don't want to wait 3 months to train the next rev of FSD. They want it in an hour, ideally, and certainly within a week. So they've got that constraint. But they have this other constraint, which is eventually they're going to want 100 times as much as they have now, 1,000 times as. And so they want to get on a track that leads them to, for them, the cheapest compute that they can get. And so this is one of the reasons why you don't necessarily want to go with a cloud service, because the cloud service is charging you some margin on top of it. I mean, in addition to wanting to control your own destiny, like vertically integrating your data center it's always going to get you a better price. So they naturally want to build their own data centers. I mean, they get better security that way. They're ultimately going to get better economics that way. And it makes a lot of sense that they would say, what's preventing computers from getting better at solving this problem for us? And is there something that we can do about that? And I think Dojo is them basically saying they see opportunities to make significant improvements on the way other people are doing this stuff right now and get themselves bigger, faster computers at a cheaper price than they can get by going out and buying what they're doing right now, which is, I mean, the real alternative they have right now is to build a big data center, fill it with super microservers that are full of NVIDIA chips. That's what they're doing right now. Yeah. And I think Elon made a comment toward the end of AI Day about, Dojo will succeed if the guys want to turn off because if Dojo is really good, then you're going to want to use it for everything.
Yeah, makes sense. I mean, it seems like, this whole idea that larger neural nets, of course, with quality data, just perform better, but you need this massive amount of compute power, to train, let's say, huge neural nets. And so there's this reality of being compute limited in sense, because, without the necessary compute power, you can't train the super large networks, which will give you better performance. So it seems like, Tesla is looking forward a lot, and it seems like they're being super ambitious with how much they want to push the envelopes.
Dojo is not a solution for next year. Dojo is a solution for the problem they anticipate having in 5 years.
Exactly. So they're pushing the envelope, saying that, hey, we're going to need, a huge amount of larger, neural nets to the point where we're going to have 100 times, 1,000 times more compute power. When they calculate the cost, they're like, we're going to give away perhaps billions of dollars to NVIDIA. And it's for a less superior system than what we could, come up with ourselves. Is that kind of like the gist of perhaps the background of why, Dojo exists?
I think that's it. So OpenAI is, they work on really big neural networks, right? They do these amazing experiments where they look to see how far does this technique scale. And they ended up cutting a deal with Microsoft.
Yeah.
There's the cost of compute for them just dominates everything. And when they look out at the things that they want to achieve, they see themselves needing billions and billions of dollars to spend on compute. Now, they don't intend to build their own data center. They're basically cutting a deal with somebody who has their own cluster and is interested in developing their own technology to do this kind of stuff. And that's a route that you can take. Tesla wants to be vertical, and they want a machine that's specialized to their needs. And probably more than anything, I think Tesla, more than OpenAI does right now, that Tesla actually sees their prospects being limited by how good the best computer is, right? It's not like, even if you could get all of the compute that you wanted at the price that you wanted to, there's a realistic limit to just how, beyond the economics, like how much you can get and how fast it can be. And as I mentioned before, neural networks, because they are a really unusual kind of computation relative to the stuff that we have infrastructure for and we have architecture for in the world today, there's this unique opportunity to actually do significantly better if you're really willing to rethink the problem. And I look at Dojo, and they've really, in some very significant ways, rethought how to go about doing this kind of computation.
Awesome. I want to in a bit go into the details, of exactly the specifics. But still talking about kind of the bigger picture here. Like, you bring up OpenAI, and I totally know what you're saying with their whole deal with Microsoft. It seemed like OpenAI has huge ambitions, but they realize they need compute power on a massive scale that they can't afford on their own, right? So they made a deal with Microsoft to give equity in the company in return for compute power. What if, let's say, Tesla's Dojo project is successful, and let's say Tesla has this massive, let's say in 3 or 4 years, this massive Dojo computer. Do you think it'll allow Tesla to do things that they wouldn't necessarily maybe were in the position to do before? For example, let's say OpenAI GPT-3, or let's say GPT-4 in the future. Like, do you think Tesla might be tempted to try something like on this kind of, kind of overlap on some of the stuff that OpenAI is actually doing with some of their huge projects, because Tesla would have the compute power to experiment into other areas than just, let's say, autonomous driving.
They're going to learn some things that OpenAI is working on. Like, if Tesla hasn't intentionally tried to just scale to crazily big systems right now, but if they really pursue FSD, and they're going to get their own kind of scale, and they're going to be answering some of the questions that OpenAI has been looking at a different way, right? I mean, OpenAI is really clearly focused on getting to AGI, what they call AGI, right? Like this idea that you can build systems that can do pretty much anything a human can do, that they think are general. And so there are architectural questions there. It's probably not just scaling. There are things that they need to learn that they might need a lot of scale to get around to learning. And it's not clear to me that Tesla is itself. I mean, who knows? It's, I feel like I was kind of wrong about the robot thing, in that we talked about the humanoid robot, but I was like, it's too much. It's not, it's not, I didn't really see how it was on the path to any of their immediate goals, but then they decided to do it, right? So, maybe a couple of years from now, we'll be sitting here and Elon will be, having AGI day, and exactly. And he'll be talking about, well, somebody's going to do it. We might as well do it. So I'm no longer in the camp of willing to say, no, he's probably not going to do that.
Yeah. Actually, one of the biggest...
That said, like pursuing those things is not, just like the humanoid robot wasn't obviously on the short path to solving any of Tesla's near-term problems, and they've got plenty on their plate already. Yeah. I didn't see AGI going there, but maybe they overlap. Or, people have asked this question a couple of times. Well, like, do you think, Dojo would enable Tesla to get into like the, selling compute as a service kind of thing. And I've been a little skeptical about that because there's a lot to compute as a service, like running AWS or running Google Cloud services, which is probably not stuff that Tesla is interested in getting into. Like it's not about just building a big server farm and leasing time on it. There's all these tools and all this management, all this sales and all this customer service that you have to get into. And that's the lion's share of that problem. It's not building a computer. On the other hand, if you were OpenAI, right, and Tesla has this giant computer, which is just made for running really, really enormous neural network models, maybe you want to cut a deal with them to do that kind of stuff, where it's a very specialized kind of cloud compute, which is, it's not for running, Tom, Dick, and Harry's, random neural network thing. It's like if you've got a really big problem and you're willing to dedicate specialists to learning how to use our hardware so that we don't have to hold your hand or whatnot. Yeah, that could turn into a good business, especially if we get into a world where, OpenAI is already trying to do all kinds of interesting commercial things with GPT-3. Well, GPT-4 and 5 and 6 are going to be much bigger and much more expensive. And if they're commercially viable, like if the concept of going further down that road is a way for OpenAI to fund themselves while they work on their stuff, then yeah, they might say, it's cheaper and faster for us to do this work with hardware that Tesla will lease us than it is to go to some other cloud provider.
Sure.
Like that, I could see happening. That would totally make sense.
Yeah. Like one of my big takeaways actually from Tesla Bot was, I think actually Tesla Bot is the move toward AGI. I really think that like Tesla Bot, it seems like just this, I won't say harmless, but this, a humanoid project that seems like way far out in the future that Tesla will do a prototype. But when I think about it, let's say 10 years down the road, I'm thinking the big part of Tesla Bot that really strikes me as super ambitious is Tesla Bot is going to be used to interact with humans on a level that's, I think, far more immersive and engaging and also much more time consuming than a computer screen. Whereas on a computer screen, you're opening up your phone a few times, or you're opening up a computer screen. The human bot can be with you all the time, talking with you when you need to talk, or showing you something when you need to be shown. It's this interactive thing where it seems like, for Tesla Bot to reach its potential, Tesla Bot is the ultimate form of AGI in a sense, because it would need kind of this human level intelligence to fully, I guess, show its benefit, right, to the human partner or whoever. But when I think about it like that, I think Tesla could be destined in a way or headed toward competing against a lot of these big companies like, Google Brain or, DeepMind, OpenAI, Facebook AI, etc., because it seems like they're all gonna intersect in some ways down the future with AGI. But to me, Tesla's taking this unique approach where they're combining hardware and software together in what they claim will be kind of this ultimately useful form of a humanoid. And that's the big bet that I think Tesla is betting on right now. And it's it's quite fascinating to see it happen.
I would talk about it a little. So there's definitely this body of thought that suggests that embodiment is somehow very important for the process of becoming intelligent, and the ways that having common sense and whatnot about the world, and kind of understanding a human perspective on things. And so I would definitely agree that to the extent that that is true, and we don't know to what extent it's true. It might be super critical and it might not matter at all. But there are a lot of people who believe pretty strongly that embodiment is an important component of like learning how to be generally intelligent. I'm going to use that term even though I really hate it. Okay, so Tesla Bot as a vessel for absorbing that experience. Okay, that's great. And if embodiment is important for that kind of stuff, Tesla Bot could definitely be an important component of that kind of stuff. There's having a humanoid form that you can interact with the world in is incredibly useful, right? There's so many things that it allows you to do that you just, it's the most useful shape that you can be for being in a human world. Like if you're going to build a single mechanism and it's going to do a lot of things, the humanoid shape is a really, really good choice for that kind of stuff. So in terms of functional utility, it's a great shape. That said, there are all kinds of other, like if what you want is something to talk to, like your cell phone, your desktop computer, your television, the Siri or whatever sits on your coffee table, those are also good forms in other ways. Like it's not necessarily a big benefit to like be in a physical body in order to have a conversation or to be helpful to people in certain ways. Like help that you're providing to people that's in the form of information, like arguably a cell phone is better. It's always in your pocket, right? So I'm a little reluctant to go to it's the ultimate, kind of shape for serving people. It's a super useful shape for interacting in the physical world in a world that was designed for humans. I think that's really true. So I would tend to like constrain my anticipation in that kind of space. Like,
Sure.
If you're sad that your puppy died, a robot can hold your hand, right? But it doesn't need to be a robot head that consoles you and talks to you about those kinds of things. So like if we're talking about being a companion, I think the movie Her did a pretty good job of making the case that, like an earpiece can be a great friend, like if what you need is a voice. And I think there's some, there's some point to that. That could be a really good form also for a different way. And of course, AI, unlike animals, unlike human beings, an intelligence isn't constrained to a particular vessel, right? I mean, the AI that's in your Tesla bot at your house, it's also in your, it's in your, your Siri, whatever thing, it's in your microwave, it's in your phone, because it can be everywhere. And AI isn't constrained to a vessel like intelligence is for biological creatures.
Sure. Yeah, definitely. So I want to actually discuss this Dojo as a service, and then we'll go into the specifics of. We'll get there.
5-episode one.
Yeah. So for those watching, James has a bunch of slides and some stuff to share on the specifics of Dojo. But on Dojo as a service, so one idea I was having today was, one of the, of course, there are a lot of things obviously to do Dojo as a service. You need all sorts of supporting infrastructure and systems, and it's probably a monster to come up with a service like that. But one of the issues is the scale, like meaning for Tesla to have a Dojo kind of cluster and to meet all their needs, it's gonna cost more than if, for example, they actually had perhaps 10 times or 100 times more capacity than they need that they could actually sell as a service. They would bring down the costs, dramatically.
Yeah, there's an economy of scale.
Exactly.
And by becoming, it's an interesting thing that we learned recently from how TSMC and Samsung have kind of taken over the chip business. And 10 or 15 years ago, Intel was definitely on top in a lot of respects. And you can make the argument that the reason that TSMC is on top now is because that was where people went to build ARM chips. And because there are more cell phones than there are computers in the world right now, TMC ended up with the volume. And it was that volume that allowed them to get ahead of the game and stay ahead of the game. It's not just, they make chips for everybody. Like they have incredible volume. And that volume has allowed them to push the technology much faster than Intel could. Even though Intel has a decent amount of volume, they don't have nearly as much as TSMC was. And that was the thing that made the difference. So I wouldn't be surprised if Elon was like, look, if we want to have the best compute at the lowest possible price, it makes sense for us to crank it out at scale so that we can drive the price down. And if we make more than we can use, then essentially selling it to other people becomes a mechanism to fund our own development to drive the cost down, because they want their compute factory or their computer factory to run at the highest possible volume to drive the cost down. So that's a way of thinking about it that I could get behind.
Yeah, that's exactly what I was thinking this morning was, at first they're gonna just satisfy their own training needs, right, with Dojo, and it'll get to a point where maybe they have extra time that they're not using, for example, training at different periods, and they could perhaps offer that on a limited basis, but it would be kind of like deprioritized if Tesla is needing to use it for other people. So it would be probably limited. But then if Tesla keep on building capacity, they have double or triple or quadruple amount of capacity than they need, then the time available for others will increase and the reliability will increase in terms of Tesla won't be needing it all the time or during certain periods. And at a certain point, it can get pretty reliable for people. And Tesla will only be using a smaller and smaller portion over time of the complete capacity. And
the economics are complicated, so it's hard to make strong statements about it without sort of looking at, where does the economy of scale benefit really kick in for compute? We know with ICs, there's an insane benefit to economy. This with cars too. The more cars you make, the cheaper you can make them. Yeah. With computers and data centers, it might also be true, but it's not clear that it's true. It might well be true, and if it is true, then this becomes an important thing.
Yeah. One of the things that stuck out was the whole Dojo processing unit, right? This DPU unit that it seems like they're already building in the programmability of this unit into it. So you could, they're kind of setting up. Yeah, they're kind of setting up this really interesting.
So that it's like HPCs are always built with a lot of partitionability because they're big, expensive machines, and sometimes you have calculations that you want to run that take the whole machine. But most of the time, what you want to run is a bunch of different jobs that don't take the whole machine. So it's HPCs, it's part and parcel of the way that they get built and operated, that they are partitionable so that they can run lots of jobs for different people. So that, because they're big, expensive machines, you want to get your money's worth. You want to keep them busy. So you want to be able to run medium-sized jobs, small jobs, big jobs, and super huge jobs. And you want to be able to run a mix of those. So, I like how visually partitionable the Dojo, the fabric is that they have. They built it so it tiles, and you just basically take strips of tiles and you break those out into individual compute nodes, and then you run computations on a chunk of this. And it's really easy to look at that and see how, if I had 25 jobs and they were these different sizes or whatnot, if I run these 5 first and then these other 3 and then these 6 after that I can keep the machine busy. You can schedule the machine up that way and have this very kind of fluid adjustability for the amount of compute that you're going to allocate to any particular process.
Yeah, definitely. It's one. The other thought I had this morning also was Tesla is so ambitious with their vertical integration regarding AI, where they're doing it seems like from A to Z, like they're getting the data themselves, they're getting, they're making their neural nets themselves, they're building all the tooling, mostly themselves. They're getting the training, computers themselves, or actually, and the hardware chips inside the hardware, right, as well. The supercomputer training, not just the chips, the hardware, but also the software that it takes to build, pull all that together. And it just seems like this complete integration is really fascinating to watch when it's not necessarily what Tesla was as a company 5 years ago, like, Tesla as a so-called car company, an EV company. It seems like this is like they're really pushing the envelope on hardware and software and neural nets and AI in a way that they've almost transformed, the identity of Tesla in some ways. Sure, they still make cars and are a car company, but they've almost built this entire separate company, with AI hardware, software experience over the years. And it's largely, I don't want to say largely, but for the general public, it's kind of gone unseen. They just look at Tesla as this car company.
Yeah, that's what gets the attention, right?
Yeah.
In public. Yeah, it is not, I'm a big fan of neural networks in particular in compute, especially as a way to, bring to reality a lot of things that I think people really want that have seemed like dreams for a really long time. They're like, because I think the potential for artificial intelligence, especially deep neural networks, are so profound. Like, I find it really easy to believe personally that 50 years from now, we remember Tesla as an AI company, right? And that, Amazon, the consumer-facing version of Amazon, it's still, it's a store, and it's a truck that comes and brings you your groceries, right? But in the business world, Amazon is this juggernaut of compute too, and their disruption of the retail business is certainly nothing to sneeze at, but they've had equally large an impact in commercializing sort of this, compute as a service thing. I think, and I wouldn't be surprised if, 50 years from now, like that's the thing Amazon gets remembered for, and not the grocery stuff.
Sure, definitely.
They're really important economic things, and they've got great legs, and we're just starting to see the potential of these things.
Yeah, definitely. Yeah, James, let's go ahead and let's dive into the specifics. The slides of Dojo, and maybe we can get some different technical kind of insights and understanding on this stuff. Okay. I'm going to switch to the slide view. Yeah, go for it.
Okay, let's see if I can flip these around. Yeah, okay. So as we talked about, we could just walk through these slides. I got... Okay, so let's start talking about this slide. So on this slide, what Ganesh is showing us is what he's calling a compute plane. So clusters, so HPCs today, the main way that HPCs get built is you have a bunch of compute nodes and you connect them together with a network. Inside the compute node, a compute node would be like a server size rack, which would, it'd be a box about this big or something like that. And it goes in a rack, and it's kind of a unit of compute. And then you have a network, usually an optical fiber network, that connects these things together. Because most HPCs work on a wide variety of problems, they need a network that allows data to move fairly efficiently from pretty much any computer to pretty much any other computer. So they have a distribution system that's basically designed so that you can take, a bunch of machines that are maybe in the same rack together, and you can have them work together on a problem. And then you can distribute those results over to a hard store, or you can take those results over to some other cluster machines that might be located more, kind of like, on the internet, you want any computer to be able to talk to any other computer. We don't do a thing with the way that we build an internet where, like, my computer can talk to my neighbor's computer, and his computer can talk to the next neighbor over. And, and if I want to talk to Cincinnati, I got to go through 8 machines. We build the network as a tree. So you kind of, you go up to a higher level of the tree, and then you work your way down a branch. And the reason to do that is to minimize the number of hops between any 2 machines, because ahead of time, you don't know what machines are going to want to talk to what other machines. So that's the way most HPCs get built today. The nodes that go in the data center are connected to a network, which is kind of like the internet in the sense that they don't heavily prioritize. Like they don't try really hard to have really good connections to the guy next to them, and they're willing to sacrifice having good connections across the data center. They pretty evenly prioritize everything, and that leads to a certain kind of structure that you have, and it leads to a system that's very flexible in that it can do lots of different things pretty well. Now, in the case of Tesla, they don't care about any of that stuff, at least not for the compute fabric. Now, the compute fabric, it's not all of Dojo, but it's the heart of Dojo. It's the core of Dojo. And the design principle of Dojo is illustrated in this diagram that we have right here. You notice that the squares, each of these squares has really good connections to the adjacent squares. But those are all the connections it has. If you want to send data from an outside system to some square here in the middle, it's got to go through a bunch of intermediaries on the way. So you don't get to go to any node in one hop, not easily. Anyway, you've got to pass through a bunch of other nodes, and then so it takes bandwidth from a bunch of other things. But if you come up with a problem, if you can structure your problem so it's like automobiles moving down an assembly line, this is great because each one of those nodes does part of the problem, and you pass the car along. So the reason that you get a big benefit from this is that all of these nodes, they can all be talking at the same time because they're not sharing their connection. Like on an internet type network, if you and your neighbor's neighbor are all trying to, BitTorrent something at the same time, it's got to slow down because there's only so much bandwidth out of your network. In this architecture, the nodes are heavily prioritized localization. Like they really care about being able to talk very efficiently to the node next to them, and they care a lot less about being able to talk to something that's much further away or main memory or something like that. So this is a really important design principle, and there's a reason why this is a really good design approach for neural networks, and that has to do with the fact that they're mainly about multiplying, doing operations on really big matrices, specifically multiplying and addition, so-called MAC operations, which is a multiply, accumulate. Those are situations where you have really big matrices and you're multiplying them by other big matrices and you're saving the result, and then you do another one and so on. And in that, because of how regular the structure of those operations is, and because these matrices are so big in neural networks that they can bridge many processors, this kind of communication architecture actually works really well. And this is an interesting thing. This is the first clue that Dojo is trying to do something different from more conventional HPC architecture. So this is the kind of thing that you don't get with a GPU. GPUs don't have this tiled architecture where you have a problem and it flows through the tiles as it gets solved. GPUs are composed of lots of processors, but all of those processors work on a problem that they fetch from main memory. And they can talk to each other, and they do talk to each other, but the most important bit of communication that nodes in a GPU does is to the outside world or to the local memory inside the GPU. It's not to the guys that are immediately adjacent to them. And so this is kind of an example of where, taking a fresh sheet approach at building a processor for doing neural networks, you can design something, you can choose architectural elements that are a really, really good fit for this particular problem, even though they make your system a lot less general. Like there are all kinds of things that Dojo isn't going to do very well, but it's going to do neural networks really, really well.
Got it. Okay, so let's talk about this a bit. So in the AI presentation, they're talking about kind of these three things: compute power, bandwidth, and latency, and how Tesla wanted to focus on bandwidth and latency. So high bandwidth, low latency. Can you explain kind of why that's so important when training neural nets, like high bandwidth and low latency?
Yeah, so high bandwidth and low latency is a different way of describing the stuff that I just talked about a minute ago. If your nodes, so there's two ways. If you look at this diagram with all these squares and these little arrows together, and we talk about the bandwidth is how many bits per second of information can be exchanged by your architecture, right? I was actually going to, I don't know if you want to call up this, these two slides were actually illustrating this, the ones that I did. You want to take a look at those a minute?
Yeah, go for it.
Because they sort of illustrate this point pretty well. Okay, so go to 1.
Okay. Got it.
Okay, Okay, so let's see. I don't know if you can see this. Let me try this laser pointer function here a second. Can you see that, Mark?
Yes.
Okay. What we have right here is I just drew. These are 4 computers. Memory inside it of much bigger external memory. So the way these work together on a problem is, you've got a description of the problem that's to the memory, and each one that hit the problem there for a while on it, and they put the result back out here. So software breaks the problem up into a bunch of different pieces, and each separate piece flows to a sensor.
Got it.
Flow back. This is how most machines that are parallel work today. So I'm going to flip to slide 2 now to do the contrast thing. So if you look here at slide 2, we see a really different architecture. Now, for these guys to load their problem descriptions, this first guy next to him, memory. But the second guy here, go here. So the problem is this. But if I build my problem so that when this guy is done, he results to this guy, and then guy results to this. My with this plus this plus this can work simultaneously. One of them can use that link, right? So go back to that first slide again, and we look at the total bandwidth in this system. All of these guys, whoops, that was the wrong one to hit. All of these guys are sharing one communicating, right? So the system is this width because only one of them can talk at a time. And each of these guys uses it sequentially. So the thing with this one link is that link. Whereas if we go back to slide 2 again, we get to add all of these links together. So we're now.
Okay, cool.
So we're done with the whiteboard. Yeah. So I've just drawn 4. So links on this particular thing. So the difference between being able to use one of those links at a time and being able to use all 4 is only a factor of 2. But Tesla has 354 of these nodes, right? Each one of them has a ½ gigabyte per second per direction. So every one of these compute nodes has 2 terabytes per second of bandwidth, and there are 350 of them on there. So there are literally hundreds of terabytes per second of bandwidth on this chip, and you can use it all because none of it is shared. It just goes from one hop to another. So if you can build a problem so that the bandwidth it uses is primarily these short hops node to node, the bandwidth is insane. It's just incredible the amount of data that can be passed along. Now, to really use it, you have to be able to do the assembly line trick, where, one way of thinking about a regular, I was thinking about this sort of factory metaphor for talking about these things. Like, you could imagine factories where factories are broken up into a bunch of rooms. And in each room is a certain size, and it has a certain number of people working in it, and it's got a certain number of tools. So the tools are the memory, and the parts that for whatever they're working on that room are part of the memory, right? And the speed of the processor is the number of guys working in the room. So they can work for so long on the stuff with the tools they have in that room and on the parts they have in that room, and at some point they finish. And then they've got to take what they finished, walk down the hall to the main memory, and deposit it and pick up more tools and more parts, and then go back to the room. So how latency is how long that hallway is, right? And bandwidth is like how much is it one guy carrying something, or do you have a forklift on a pallet, or do you have a semi, right? How much stuff can you move at one go? That's the bandwidth. In this case, what we have is we have a factory where we have a bunch of rooms, and they're one after another. So each hallway just links to the next room. But we never change the tools in the room because it's an assembly line. So, at the start of the shift, everybody gets their tools, and they don't have to get parts because parts come in along with the thing that you're working on. You work on it, and then you pass it out the hallway to the next thing. So if you can structure your problem like an assembly line that, which with neural networks you can, more than almost any other kind of computation which is widely done today, neural networks that are extremely amenable to that kind of construction. So unsurprisingly, this is the shape of the factory you want. You want an assembly line. You want lots and lots of assembly lines because all of your problems break down into this thing, which can be basically a processor can work on part of it, and it can pass it down to the next processor, which can do the next part, and so on.
Got it. Yeah, I mean, that's actually pretty crazy. I mean, that's a fabulous job, I think, in describing like the difference of approach right there. I mean, it seems like rather than having to like go back to home base every time after doing a job and traversing, that path, if you could find a way just to, actually, as you're saying, don't go to home base, just go to the next slot, the next place, you're going to save that whole traversing back, to home base and back. And it seems like neural nets is like the perfect thing because fundamentally a neural net is processing thing and then and sending those results to the next level, neural nets and doing that. So, I mean, it seems like it's fundamentally like if you can customize right? The structure of how your chips are set up, where you're they're just passing it on to the next kind of sequence. And it seems like that's like, is that kind of the essence of Dojo? It's like, it's basically.
This is a really big part of it. There's other things about it too that are actually, and I think equally impressive, but this is a good slide to start with because there was a time back in the 80s when people tried building computers this way. They had this idea that networks are so slow compared to the processors. This was first a problem back in the early 80s. And so they had this idea that the way to get more bandwidth, to get more total bandwidth, is just have every processor talk to its neighbor instead of having everybody share this big network that gets congested. And the thing is, the processors, they weren't general enough. They fell out of favor because people found it really hard to take video games and weather calculation, like all the stuff they wanted to work on, like reformatting the process, reformatting the program, like what you were doing with the algorithm so it would work on this. It just turned out to be too hard. And so this whole architecture, it fell out of favor. And really, nobody's gone back to doing this kind of stuff for sizable computers. I mean, there's a few exceptions and corner cases and stuff like that. But for the most part, nobody has done this. And so now we have neural networks coming down the pipe, and they're doing matrix math, and they're doing matrix math on these enormous matrices, like really, really big matrices, like matrices that are so big they can span multiple processors. And all of a sudden, we're back in a world where, hey, this actually makes sense. Like, this is a really good fit to this particular problem. Mm-hmm. But as I said, it's not going to be good at a lot of other things aside from neural networks, but it's going to be really good at neural networks.
Yeah, no, that makes sense. I mean, especially if neural nets are kind of, more set up, to be processed that way. Let's dive into the next slide. I'm like fascinated by all this stuff. This is like fantastic.
Okay, so now we're talking about a single node. So just to kind of recap, Dojo it's a node on a D1 chip, and there's 354 of these nodes on a D1 chip, and they're actually in an array, which is like 18 nodes by 20 nodes. There's a total of 360 total nodes, but 6 of the nodes are removed for something having to do with networking. Like, I don't know exactly what the details are, but so they end up with 354 functional nodes on this. Then, 5 chips go inside a tile, and then there are 120 tiles total in 10 cabinets, which forms two full sets of.
Isn't it 25 chips on one tile?
There's 25 chips on a tile.
Okay,
Did I say something different?
I think you said 5, but yeah, 25. Okay.
Yeah, it's 25. It's a 5 by 5 rectangular grid. Mm-hmm. So all this stuff goes up in these sort of rectangular subunits, or square, more or less square subunits. So the nodes themselves, if you looked at we'll see this picture a little bit later, but the individual node, they actually made the node, the design of the node, so that it's a tile. Like once you design a single node, you can literally replicate it across, because the left edge of every node fits just like a puzzle piece into the right edge of the adjacent node. So when they do, this is actually brilliant. When they do the IC design, they just design this one little part, and then they literally make hundreds of copies of it, right? So that makes their mask costs will come way down. Like, this is, in a lot of ways, it's a very easy IC to design because they've made it incredibly regular. So anyway, what we're looking at on this slide is what's in one of these nodes. So this is, this 1.25 meg of SRAM, this is the toolboxes and the local parts for the guys working in this room of the factory. They have, they don't show, there are matrix multipliers. They have 4 matrix multipliers here, these 4 red things. Each one of these is an 8 by 8 matrix multiplier, which I believe it's taking in 8 CFP8, which is basically, it's a 8-bit floating point format. So it takes in an 8 by 8 grid of those. And in a single operation, it can take an 8 by 8 square matrix, multiply it by another 8 by 8 square matrix, and then also do the accumulation on that. So basically, you take matrix A is an 8 by 8 matrix, matrix B is an 8 by 8 matrix. The output is a different 8 by 8 matrix, and you're basically taking the first matrix and the second matrix and multiplying them, and then you're accumulating the result locally. So after this, you can grab another 8x8 matrix and stick it on there, multiply it again, and continue to accumulate the results locally. That's one operation that you could do. Neural networks are they're 99%, sometimes a lot more than 99%, just multiplying these giant matrices. But then there's this other 1% of stuff. And if you can't do it, you can't do the neural network. So you have to have some other functionality in the node, which is a lot closer to what a general purpose CPU does, because a lot of it has to do with like figuring out where things are in memory, doing moving stuff around in memory, and you've got these other sort of vector operations that you want to do, and which might be, for instance, when you do neural networks, a single neuron, you do a multiply accumulate of all the weights times all the inputs in a single neuron, and then you have this nonlinearity you apply, which might be like in the shape of sigmoid, or it might just be this. Neurons basically do this thing where they they get a bunch of inputs. They might have 100 or 1,000 inputs, and then they multiply them by the weights that they've learned that they're supposed to apply to each of those inputs. After they do those multiplies, they sum all the results together and they get one number. And then they have a threshold, which is like, if it's bigger than this number, then I'm going to fire, I'm on. And if it's lower than that number, I'm not going to. So that's what we call a nonlinearity. Instead of being a smooth transition, it has a threshold. And once you go over that threshold, the output goes up very quickly. So to do those operations are not just matrix multiplies. They're these other things. You need to be able to do them. And that's what this 64-bit superscalar CPU is. Okay, so the other important thing that we have on here is this low latency switch fabric. So the links between these adjacent nodes, they basically, on each one of these nodes, you have a little sort of network device which can talk to the nodes to the north, south, east, and west of this node, the four edges. And that's what this little switch fabric thing is here. It's designed to basically allow you to send information straight across. The switch fabric itself is like a little standalone processor that just handles the communication for this. And then it can take stuff that's passing through that and write it into this memory. So the local processor works off of this local memory. It can send instructions to this switch fabric. And then the switch fabric itself can talk to the switch fabrics of the adjacent units. But in order to be able to do all of the weird corner case things like pooling, or you want to do normalization of data, there's other stuff that goes into that 1% of stuff that's not a matrix multiply. And all of those capabilities are built into this other more flexible, more general purpose compute box that they have here in this purple square. So what Tesla's basically telling us here is they built a simple processor that's wide and it has a high clock rate. It runs at 2 gigahertz, but they're not getting too fancy. They're going to keep the compiler relatively simple, and it's got a wide bus capability. So it fetches data in pretty big chunks, but it's not doing a lot of really fancy stuff. You'll see it's gotten a local cache. They're not trying to do anything really complicated with this. They want a relatively simple processor that handles big chunks of data and does relatively simple things with it. At the node level, the nodes are designed so they talk to adjacent nodes. This multiplier is also built the same way. We know that that's true because that 1.024 teraops of compute cannot be achieved if all of the parameters for all of these matrices have to be fetched and stored on every clock, because the buses they have here don't have enough bandwidth to do that. Because we know they don't have enough bandwidth and they're claiming this high processing rate, we know that the matrix multiplier itself is inside the matrix multiplier. It's doing the same trick where you've got a matrix multiplier. You put both matrices in to start. You do your first operation, and then what you do is one of the matrices you just shift down a row. So on each clock cycle, you only have to load one row of the matrix in, and yet you get to do your 64 multiplies and 64 accumulates on the next clock, even though you're only loading 8 new values in, because the other 7 rows just clock down. They just step down one step in the same multiplier, and you do the same operation, and then you can accumulate in place. they've built this puppy so that it can do matrix math really well, and that's true all the way up at the top of how they build the fabric, and it's true all the way down to these individual matrix multipliers down inside these individual nodes. Yeah, so this was Ganesh's chart, basically bragging about their bandwidth, and it's kind of interesting, because there's two different ways you can talk about bandwidth on this thing. Like, if you have a square matrix, if you have a square grid of nodes, what is my bandwidth? Is my bandwidth just how much goes from one edge of the grid to like the next die over? Or is it the bandwidth of all the interconnects in between? Well, so I noticed when I was looking at Cerebras, so Cerebras is another company that they do a wafer scale processor. And Cerebras, when they talk about their bandwidth, they add every single connection between every single die. And so they get these crazy high numbers like 12 petabytes per second. I think it is. It's like 12 petabytes per second of bandwidth. So Tesla is just talking about the edge bandwidth of their processor, because if they talked about the real bandwidth, this vertical, you wouldn't be able to see these other guys on this scale, because it's like 300 times higher than this. Or no, I guess it's like 20 times higher than this. So it would just look ridiculous and nobody would believe it. So they decided to define see, over here they describe it as off-chip bandwidth. So this is how much you can get off of one edge or off of all four edges of the chip together. But it's kind of not a super fair comparison, because their bandwidth is actually much higher relative to these other guys on this chart. So this is one compute plane for Dojo. And Ganesh here, he's showing how they connect all this stuff together. So this is 1,500 die. So we talked about the diagram we were looking at before was a node. And there's 354 of those nodes on a single die. That's the D1 chip is a die. If you look closely at this picture, you can see that it's kind of broken up into 5 by 5 chunks. So each one of these is a tile. So you can see this is 3 tiles down, and this is 20 tiles across. So this is a total of 1,500 die. And this is a single plane. This is a single compute plane. So on each one of these die, you've got, 10 terabytes per second moving sort of laterally. And then when you get to the edge of the die, so you can hop off it and go to the next die over, you're restricted to 4 terabytes per second. When you get to the edge of the die, you lose a little more than half of your bandwidth, right? Because you've got 10 terabytes and you got 4 going out. So 40% of your bandwidth makes it to the next die. And when you get to the edge of the tile, you lose a little more than 50%, because you go from 20 terabytes to 9 terabytes. So you can see that because of these bandwidth constraints between the die and then between the tiles, when you structure a job to run on this, ideally you want to try to make it fit in a single die if you can, and if you can't, make it fit in a single tile, because you get so much more bandwidth on there. As soon as you go out of a tile over to the next tile over, you lose another 40%. Now that said, they're losing a factor of 2 more or less at each one of these stages. And something to keep in mind is that regular HPCs lose a factor of 10, right? So even though this Dojo fabric is definitely encouraging you to keep stuff in a single tile, if you have a job that's big enough that it can't all run in one tile, and it's got to straddle 2 tiles, okay, you get a factor of 2 reduction for the chunks of the data that have to move between the tiles, but it's only a factor of 2, right? It's not a factor of 10. So he outlines here that they have higher radix connections, which is a lot of times there are some kinds of operations that you want to do where you don't want to have to daisy chain through like all the processors. So they have some other connections they've added to give the network more flexibility to have shorter hops between for some kinds of operations that you're going to want to do. And this is in addition to the low latency mesh that he mentions here. So this is a physical description of a tile, right? So these are the interconnect links they have on the end. The individual D1 die, they get flipped upside down because the connections all come to the top. They get flipped upside down, and then they go onto a set of contact pads on this other silicon wafer. And this other silicon wafer, it works like a printed circuit board. The high bandwidth connections, the 4 terabytes per second that come out of each one of these die, run across this short gap on this piece of silicon to the next one over. Okay.
Got it.
So the significance of this slide is Ganesh is showing us they made a die, they made a tile. It's working well enough that they can train a neural network on it. And to the people in the audience, they know this is a ton of progress. It's pretty common to get a die back from the factory when you fabricate your first chip, and for it to be a year before you can run real code on it. There's a lot of work between those two. A lot of it you can do ahead of time. Ganesh here is basically showing, like, this is real. It's going really fast. Like, this is pretty amazing progress that they can actually run, like, real neural networks on this thing right now. I mean, they're training GPT-Min, which is it's a sizable language model. So here he shows how partitioning works and how you can do partitioning kind of logically. So this is a slice at the corner of that fabric we were looking at before, where each one of these is a die. You can see that they have dedicated memory for each one of these die. So each one of these columns can be treated as a standalone compute unit with its own memory and its own interface to the host. So when you want to partition the Dojo fabric, you can take a chunk of it, just a column or a group of columns, and you can allocate them to a problem. And so it's a fluid partitioning scheme that runs along the physical boundaries of these die. And I suspect they can probably partition at the node level also, but it's not unlikely that if a job is small enough that you can run it on a node, that you run it on some cluster. You don't need Dojo for it. After this, Ganesh starts talking about the maturity of their software stack, their compiler, the tools that they've built to make this thing actually usable as a system as it comes online. Basically, running one of these systems is complicated. That 1% that's not matrix multiplying, it includes many, many, many flavors of things that you need to be able to do passably well so that they don't become this Achilles heel for your system. And in order to accommodate all of those things, they've built a lot of software to try to map those things onto the hardware as efficiently as they can. And so he's showing various ways that they've built software tools to be able to take a job that they want to do and map it onto the hardware that they have. This is more of the software stack thing. And this slide is more about showing us the maturity of the software stack that they have right now and the level of ease of use that they aspire to get to. I think later in this thing, he has an example where essentially, they want their software to be able to partition. They want, a neural network developer that wants to train a neural network to be able to just say, I have this device. It's called a Dojo device inside PyTorch, and run your PyTorch description of your neural network kind of directly on Dojo. And the rest of this infrastructure takes care of all the rest of the stuff. It figures out how to batch the data, how to sort the data, how to organize it, how to make it run efficiently on, individual nodes, dies, to partition it, on boundaries of tiles and that kind of stuff to the greatest extent possible. And they've also built, they have debuggers and compilers and the whole stack all the way down to the bottom. So this is a lot of work. This is definitely not trivial. Now, they're building on top of a lot, like LLVM is a mature, adaptable, configurable compiler system that is relatively adaptable to new architectures and whatnot. But that said, getting LLVM to run well on a new processor with a new instruction set architecture is very much not a weekend project. It's something that takes a bunch of smart guys that really know what they're doing a significant amount of time to do. And Ganesh is basically implying with all these slides that they've done this work, which I would not take to say that it's polished and optimized, but just having it at a point where it works now. And the slide we were looking at before where Ganesh is showing us results, it kind of suggests that they've got a significant amount of it running well enough and debugged well enough that you can actually use the hardware. So you have this fabric, you have this 2D fabric that you're mapping your matrix operations onto, right? Now, the reason that you want to do that is because I have a certain number of teraflops of compute power, right? And the reason to have a really fast network and to have all this software that arranges it so it fits well is so that you get to use as many of those flops as possible, right? And this is kind of non-obvious probably if people aren't in here, but NVIDIA, I think I did these numbers, I worked out these numbers so Tesla's existing cluster, it's 720 nodes of 8 by A100 NVIDIA chips with 80 gigabytes on board. So I looked at the stats on this. I figure they paid about $150 million for that. So that machine is 1.8 exaflops peak. That means if you had a problem where your network wasn't constraining you and all of the NVIDIA chips could run flat out, how many flops could you get? And the answer is 1.8 exaflops. So I took this benchmark neural network and I looked up statistics on how fast it ran on these various architectures. So I could figure out how much of those exaflops do you actually get to use. So, and the short answer is if Tesla wanted to try to use this entire cluster on a single network, they're only going to get 10% of that. It could be less, it could be 5. So depending on the problem that you want to run and how big the system is, and these are actual benchmarks run on actual NVIDIA systems that use the same interconnect and the same chips that they've got here. The smaller the number of NVIDIA chips you use and the smaller number of nodes, the easier it is to figure out a good way to partition the problem. The more nodes you use, the harder it is to do it well, and the more network gets involved, and so that slows it down. So if you run just on a single NVIDIA, if you run just on a single box with no external networking, and it's just the GPUs in that box talking to other GPUs in the box, NVIDIA can get about 20% of this peak exaflop rate, of their peak potential speed. So each one of these A100 chips is 312 teraflops potentially. And what you can get if you try to use 8 of them together on the same problem, and this is using data level parallelism, which is by far the easiest kind of parallelism. It's the one that's most amenable to the restrictions that this NVIDIA architecture is applying. If you use that system, you can get in the real world, you can get 20%. So of that 312 teraflops, you're only getting to use 60 teraflops of it. The rest of the time, the system is waiting on latency. It's waiting on bandwidth. It's waiting on all these other things. 80% of your processing you're losing because the network can't keep up. Okay, I worked some basic numbers. Now, there are no benchmarks for Dojo, obviously, that I can get my hands on. But when I worked out, I looked at comparable inference level architectures that are out there. Because the TPU is an inference platform which has, at the die level, it's got a similar kind of interconnect scheme in terms of adjacent nodes and that kind of stuff. I think that they can get around 80% utilization instead of 20% utilization. That's my best guess about what's going on with this stuff, looking at other similar architectures. And now there's all kinds of details, and we'll have to wait and see what actually comes out. But I think that it's Tesla's ambition to get 80% out of it. So if you compare 20% that you get from the NVIDIA thing to 80%, which I think is what Dojo's aspiration is, you get 4x performance right here. I think that might be where that number is coming from.
So one of my big questions is just kind of timeline. So it seems like, this is a huge project. Elon a year ago, or a little over a year ago, was hoping to be kind of up and running after a year. I mean, they did show kind of like, the basic, thing working. But in terms of like, what do you foresee as the rollout? Like, are they still far off from actually using this in actual training, or do you think in the next 6 to 12 months they'll actually be able to make an HPC like computer and do significant training on it?
Man, they're moving so much faster than, like, if you'd asked me, I'm sure if I'd known where they were a year ago and you'd asked me if they would be here by now, because they're moving really fast. I mean, this stuff is happening really quick. You don't get new, HPC computer architectures designed from the chips all the way up and, like that's a 10-year thing normally, right? That's not a 24-month thing normally. It seems to me like they're moving really fast. You know, if I was going to judge it based on what I think, you know, other companies do, I would say that they would be, you know, 2 years away from like actually running lots of jobs at scale and having this as an economic alternative to the other stuff. But, you know, at Tesla speed, maybe that's 12 months.
Yeah. I mean, in your opinion,
6. I don't know. It's so hard to say.
In your opinion, like, is this, I want to say pretty much a sure thing, but are you super confident that this is going to actually work, that all the benefits will actually be realized, or do you think there'll be some big challenges?
They ran GPT Mint on it. They trained that network on it, right? It works. Now, how much of the performance that they, you know, they know what the die costs. They've built a tile. They know what the performance, you know, stuff is. If they've built the compilers, they've already thought through the partitioning problem. Like, can we partition these things? We know the nonlinearities all work. You know, are they getting the performance that they want? Do they think that if they're not getting the performance they want, how much of that is that the compilers aren't good enough yet? How much of it is that the outside software isn't good enough yet? Yeah, it's super hard to say. I mean, it works, right? Sure. But will they get to the performance node that they want to get to? I cannot say. I look at the architecture and I don't see anything in the design of the architecture that makes me doubt that you know, if it works the way they want it to, it's going to be a really big deal. I actually think the single biggest unknown is what is everybody else going to do, because Dojo doesn't exist in a vacuum, right? If it's a couple years before Tesla can start moving significantly, and that's a total wild guess, right? But if it's a couple years before Dojo is really making big contributions, Tesla has to balance that against like what's the latest NVIDIA system and what have the startups done in the meantime, right? Because this isn't done. I mean, they're taking advantage of low-hanging fruit, as I described here, because they're doing a clean sheet design, and that has huge advantages, right? But somebody else could do a clean sheet design too, and you know, this is not Tesla's you know, main focus. It's not their main area of competence. Another company could do it better. Like that's not outside the realm of possibility. And I kind of feel like looking at this, the biggest question in my mind about whether it's successful or not is whether it's relatively successful. Like, is it the case that 5 years from now, this is the best option they have? And that mostly depends on what other people do, I think.
Got it. So what's kind of, in your opinion, possible offshoots? Like, by learning, let's say Dojo, they press on, they have, you know, the D2 chip, the D3 chip. Let's say this cluster, actually, there's HPC thing actually works out. They switch their training over. Do you foresee any like really kind of unforeseen benefits? Like, for example, their hardware 4 or 5 chips, I'm guessing they'll have learned something from chip design and stuff to, you know, apply perhaps to their car chips. But is there anything else you think that, you know, this whole focus on the actual hardware would enable Tesla to do that maybe few people really are seeing, you know, the potential for?
Well, it's got all of these things have great synergy, right? I've got, is it Charlie Miller? Well, synergies can often provide surprising results. And I wouldn't be surprised if the synergy between what they're doing with I mean, the fact that Tesla did their own software resulted in this situation where they're more immune to the chip shortages than all the other, automotive OEMs are, because they develop, they control enough more of the stuff that when they need to change, they can. They have the in-house expertise to do that. And, that's a synergy that probably nobody thought about before the pandemic happened. Like, hey, what if we had to suddenly change all these things in the car? Like, it's definitely a benefit, but would anybody have thought that that was going to materially affect Tesla's prospects? Probably in the absence of a pandemic or some other catastrophe that destroys supply lines, you don't really get to experience that. I could imagine. I mean, I would expect there to be synergies, but I wouldn't be surprised if they happen in these, unexpected ways. I mean, knowing chips is a super useful thing, and the more of this stuff they do, I mean, silicon is so important these days to stuff. Could they do socks for their own cars? Yeah, maybe they could. Like, what would that be like? I mean, the socks they use for the entertainment system. The chips they buy are probably pretty well suited to that, but they buy a lot of microprocessors, and like, could they consolidate a lot of that stuff? Maybe. It's I don't know. It's really hard to say. There's so many possibilities for it. It seems like there are bound to be some.
Yeah. I mean, like, it seems like the most low hanging fruit, or one of them, is just the whole integration of software and hardware, kind of like what Apple does, where you're able to match, the OS with the hardware and really optimize it. But I mean, it's like for
like what they're doing with their, like, I didn't think that they were going to be able to get so much more. Like, I'm shocked at how much better the M1 chips are.
Yeah.
Because, Intel's not a slacker. They're not sitting in the corner sucking their thumb. I mean, they do good stuff. And the M1 chips are just crushing them. And it mostly comes down to Apple knows what they need. They know what their users want. They know their application space. So when they got to where they could make their ICs, they were able to take all that stuff they knew about the domain that they need these ICs to operate in, apply that to the IC, and blam, boy, they're just crushing competition suddenly. So could Tesla do that? Yeah, they already did. The FSD chip is a great example of that. How many more opportunities are there for them to do that, in their vehicles or in their other operations? Like without knowing more about their future plans, it's pretty hard to speculate. But yeah, it's a long lever. It's a big hammer, you can do a lot of stuff with it.
I mean, and especially like when you have a kind of the leader doing this like really ambitious integration with software and hardware and pushing the envelopes with full vertical integration, then it makes it tougher for the competition, I think, to try to compete against that, because you've got this leader that's competent, and they're pushing forward.
It raises the bar.
Yeah.
It would be nice if the competition stood up and brought their best game to this, because we'd all benefit if they didn't, give up. If Tesla ends up just raising the bar for what people expect, and organizations respond to that challenge by improving what they do, then that would be great. I would love that, because the alternative for the rest of them is to just like die or become, get supported by the government and turn into, jobs programs for, union workers or whatever.
All right, James, thanks for the chat on Dojo and all your thoughts
Good
on
job
all
hanging in
these
there.
things. Yeah, it's been fantastic. It seems like definitely Tesla AI Day, it just has many layers to it,
Yeah.
The more you go into it.
Yeah, boy, you think I ran on now? Wait till we start talking about the neural networks.
Yeah, exactly.
You have been warned.
Awesome. Thanks. And we'll be in touch. I'm actually headed back to Texas soon after spending the summer in California. So going to do a couple week road trip. And then hopefully maybe when I land in Texas, we could talk more about neural nets and some other things.
Okay, cool.
Awesome.
Great.
Okay.
Well, have a nice drive and have a nice trip.
Thanks. All right. I'll see you.